Picture a robotic arm wielding a scalpel, performing remote surgery on a patient thousands of miles away. The precision required is absolute. To make sure no one else takes control of that arm, the machine has to prove its identity to the network. Right now, almost every connected device does this using software-based credentials, long strings of ones and zeros that act as a secret digital identifier. But digital identification has a fatal flaw. It is perfectly, infinitely copyable. If you can read the data, you can duplicate it. If a hacker manages to steal that binary sequence and copy it, the network is blind to the difference. To the hospital server, the attacker's laptop looks exactly like the legitimate surgical robot. We see this vulnerability threatening modern infrastructure right now. Researchers are securing autonomous drones, entire Internet of Vehicles networks, and digital twin healthcare databases, all systems where a compromised credential could lead to physical disaster. As long as a secret exists as software, it can be stolen. To actually secure these systems, we need an identity that is physically impossible to clone. Look at a human fingerprint pressing against glass. It's a biological signature that belongs to one person and one person only. Even identical twins, born with the exact same DNA sequence, have different fingerprints. That is because their prints are not dictated by a rigid genetic blueprint. They are shaped by chaotic, microscopic variables in the womb, like fluid pressure and slight movements. We can apply that exact same concept to silicon. When factories mass-produce microchips, they use incredibly precise lasers. But at the microscopic level, absolute perfection is impossible. Down at the atomic level, wire thickness varies by nanometers. A copper trace might have slightly higher electrical resistance than the one next to it. Every single chip emerges from the assembly line with its own unique landscape of microscopic flaws. Computer scientists have figured out how to measure these random manufacturing defects using a specialized circuit. They call it a Physical Unclonable Function, or PUF. Instead of trying to fix these errors, engineers are repurposing them. They turn those tiny imperfections into an unforgeable hardware fingerprint. Think of a PUF like a highly suspicious bouncer. Instead of asking for a password, which someone else could overhear, he tests your physical traits. To connect, a server sends an electrical signal into the chip's maze, called a challenge. Racing through the silicon, the pulse is delayed and split by atomic variations. It emerges as a unique electrical output, the response. Only this specific chip could produce it. You could hand a hacker the exact blueprint of the chip, and it wouldn't help them. Human engineering simply is not precise enough to intentionally place atoms in the exact wrong spots to recreate the errors. Security abandons the idea of proving you know a secret code. It becomes about proving the physical existence of your hardware. This moves the baseline of cybersecurity away from fragile math equations and grounds our safety directly in the laws of physics. The threat landscape is evolving quickly. Hackers are already using machine learning to try and predict how these physical circuits behave. In response, academic researchers are building advanced hybrid PUFs that scramble their own internal states to resist those prediction algorithms. This hardware-level defense becomes critical when we look at the post-quantum horizon. In the near future, quantum computers will be able to crack traditional mathematical identifiers in seconds. But a quantum computer cannot forge a physical defect, rendering those attacks useless against hardware identity. Soon, billions of new sensors will come online to manage our power grids, drive our vehicles, and monitor our health. Securing them means leaning into chaos. The unavoidable mistakes made in clean rooms give us a world where every connected device can possess its own unhackable, physical identity. So the next time you hear about a massive credential leak, you can sleep a little easier knowing that a vital layer of our digital security is being grounded in these microscopic imperfections. Thanks for